Thank you very much. It's nice to be back in Singapore and nice to finally also be at this conference for as many years that it already exists. No, so she already said the title of my talk is iOS 10 Kernel Heap Revisited. So when the CFP for GSEG was released, I was thinking about what to submit, and I fastly got the idea that I would submit on the iOS kernel heap. The reason for that is that my last talk about the iOS kernel heap was around the time of iOS 5, and a lot of details had changed between iOS 5 and iOS 9, which was the one that was available at the time of the CFP submission. And a lot of changes have not been documented anywhere. There are a few changes that got documented by, for example, Tajay Mand in the Azimuth blog, but it's only just one thing. Then, depending if you follow some certain jailbreakers on Twitter, you might have seen some tweets about certain things that changed. But there was absolutely no central place, at least a public place, where you would see all the changes that were made to the heap between iOS 5 and 9. Of course, I wanted to make the talk more interesting, to get voted, so I said it's the iOS 10 kernel heap revisited. But of course, at this time, there was actually no iOS 10, so I didn't know what I was getting into. The interesting thing is, when I submitted, I assumed that Apple would do the Apple thing. Just from version to version, they would change some things, some slight things. And so I expected that when the beta is released, that they would have changed a few things, but it wouldn't be major changes. Oh boy, was I wrong. We will see later that they actually made bigger changes to the heap between iOS 9 and 10 than in most of the steps before. So a little disclaimer, kernel research, especially on new systems like iOS 10, is quite hard because there is no public jailbreak, and I really don't like traveling with private jailbreaks to countries like Singapore or so. Sorry for that. So that means that most of this research was done while I was traveling, and I used most of the time macOS Sierra for that. But I then took a decompiled kernel and compared, and the heap implementation is more or less identical. So whatever I'm saying, it might be slightly wrong because I mostly concentrated on Sierra, but it wouldn't be too wrong. Also, keep in mind, the whole thing is beta. Apple keeps sneaking in changes, sometimes in the very last beta. They used to always fix security bugs in the very last beta, but in the past, as we will see later on, they put one big security mitigations in the very last beta, so it was not available for us earlier on, but we come to that later. So the agenda of this talk is therefore, first I give you a short reminder what the iOS kernel heap is, what it looks like. Then I present shortly about how it looked like in the iOS 5 days, before all the changes. And then I'm going through all the changes between 6 and 9. And in the end, you will see what's upcoming in the kernel heap for iOS 10. So what is this iOS kernel heap? If you have prior knowledge, this will be nothing new. So normally when we talk about the iOS kernel heap, we usually assume we are talking about the zone allocator, because that's the most used allocator inside the kernel. And the idea of the zone allocator is that all the heap memory is divided into zones. And the idea is that a zone groups memory, groups allocations of a specific size. So there's one zone for this kind of memory, one zone for this kind of memory, and so on and so on. It's furthermore that inside a zone, when you create a zone, you define how big the elements are. This cannot change during the runtime, so all elements inside one zone are always of the same size. When you look at the code, you will see that they are used like this. When you try to allocate something, you tell the allocator, oh, I want to allocate something in this zone. And when you free later on, you have to also tell it, oh, I want to free this pointer, please put it back in this zone. The reasoning for that is that from a pointer, the kernel does not know what kind of zone this belongs to, so the caller has to keep track of that. With the zone allocator alone, there's no way to have a variable length allocation because everything needs to be the same size. When you run OS X or iOS that is jailbroken, you can run the tool zprint, which will give you an output of all the zones that exist in your system at the moment. And as you can see, there are a lot of them. And this is just a short, subtract of all the short extract of all the zones, and you can see they have actually names, and these names are internally registered. So from the name, you usually already know what kind of data element is in there. The kalog one you see here is special. We'll come to that later. So inside the heap, in the zone allocator, all the memory that is given back by the zone allocator is from the zone map, which is a region that the kernel registers or reserves in the physical memory space, and it's about a quarter. The default is a quarter of the physical memory size. So on a 1 gigabyte system, this zone map is reserved to be 256 megabytes. It's reserved very early on during the kernel start. So in the past, the problem here was that because there was no ASLR, so the position of the zone map was kind of, predefined. So now when memory is returned by the allocator, it's returned from pages that are from within the zone map. And a zone always has a number of pages assigned to it, and whenever a zone is full, it has to grow. And for this growing, there's a specific allocation size defined. So most zones, or at least in the past, would always grow by 1 page at a time when they ran out of space. But in reality, inside the kernel, how big this allocation size is determined by a very simple algorithm that just tries to find out between 1 and 5 pages what is the optimal way to grow. Because keep in mind, every element in the zone is always the same size. So when you initialize a zone with 100 byte objects or so, and you have a 4 kilobyte page, then you have 96 bytes in the end that are just lying around. So basically the kernel heap decides when it starts a zone if the waste of 96 bytes in this case can be optimized by making the allocation size 2 or 3 or 4 or 5. The other thing that is only visible on later versions is that on all the new 64-bit devices that have a lot of memory, I believe the cutting point is 1 gigabyte. So if a device has more than 1 gigabyte of memory, the kernel suddenly switches to 16 kilobyte pages. So kernel memory is 16 kilobytes, sorry. And all the other devices use normal 4 kilobyte pages. So now you would wonder, okay, but we always need some kind of dynamic length allocation. So how does that work? This works by not using the zone allocator directly, but instead the code has to use things like kalog or malloc. So kalog is a wrapper around zalloc. And the idea here is that it allows dynamic allocations. We will see later how. But the caller of kalog and kfree must remember how big the block was he was allocating. And when he frees the block later on, he has to tell the system, oh, this was a 100 byte block. We see later why. malloc, on the other hand, keeps extra internal metadata. So malloc is just like you normally know malloc and free. You just give it a pointer and you allocate a new free. Another nice thing that most people actually don't know about is that by default OS X and iOS come with kernel boot arguments that allow kernel heap debugging. So for security researchers, these things that you normally are interested in is the so-called zone corruption logging that you can activate by using the -ZC boot argument. And when you do that, you can select one zone that you would like to log in. You select it by name, for example, kalog.128. And you can specify how many entries you want to keep in that log. So the thing is, in iOS, you cannot really make use of that without a kernel exploit because Apple does not allow you to specify boot arguments. But the moment you have a jailbroken device and you can execute code in the kernel or can at least corrupt memory in the kernel or change memory in the kernel, then you can activate these features on the fly and actually make use of them in iOS. In OS X, you just set these boot arguments and then you reboot your system, and then you can do the same thing in OS X. So let's say we activate this corruption mode logging. What happens then is that basically the kernel allocates one block of memory with the amount of records that we specified, and then it starts recording every single allocation, every single deallocation. It starts to record the pointer that was allocated or deallocated. It starts to log the backtrace at the moment of the allocation or deallocation. This is very nice for you as someone who wants to do control of the heap layout, because you can record the heap actions and you can see, oh, my exploit is not working because that strange code path actually allocated something. So let's try to make it not allocate this or do something else. The thing is, internally, all of this is stored in a so-called BT log that in earlier versions of iOS has always been just a linear list for a round-robin list, so a ring buffer, and you can just dump it. So that's the problem here. Apple does not provide you with the facility to get this out of kernel memory. So as a researcher, you have to get it yourself out of kernel memory. When you do that, you can do a lot of analysis with this. And I presented before that I have this visualizer for this thing. So this here is basically a little JavaScript tool that gets a log and visualizes what it sees. You can see here the pages that were allocated. The different colors means they were allocated with different code paths. The blue stuff are basically free blocks. And when you hover over something, you can see the backtrace. The backtrace in this case is symbolized by just looking at the symbols from the kernel debugging code that Apple releases for OS X, because this here is taken from OS X. On iOS, you can just do the same and just symbolize the kernel yourself or use some tool to port symbols from OS X to iOS. And then you have also nice names for the backtrace. What you see here is something I do during my iOS trainings. What you see here is basically the result of a kernel heap feng shui. You see that someone filled a whole heap with data, and then you see in regular intervals, you see free blocks, the blue ones. So every third block here is basically freed to prove heap control. Okay, so this is a general idea of what the heap looks like from a user's point of view. Let's go to the internals. And internally, and don't be scared of this, a lot of code here or the structure, there's not much code on the slides. The idea here is to tell you every zone that is registered with the kernel, the information about this zone is stored in the zone structure. That looks a lot like this, but this changed over the years, and this here is actually stolen from the 10.7.5 source code. That is around the time of iOS 5, but around this time, the iOS source code and the OS X source code were not so synced. So this structure is most likely not exactly the same that is used in iOS, but it looks very similar to this. what you can see here mostly is that a lot of this information is what you get to user space when you call this setprint utility. And the other stuff is mostly for dealing with the zone internally. Interestingly here is that all the zone structures are stored on the zone heap itself. So there's a zone called zones, and there all the zone structures are allocated into that. It's a chicken and egg thingy. Okay, now let's look at more detail. When you have a heap, you have always allocated and not allocated blocks. And the idea here at around time of iOS 5 is when you have a free block, then the block is basically not cleared. You have a pointer in the beginning of that block that is a pointer to the next free block. And in the zone structure, there's basically a pointer that points to the very first free element. And the idea here is, for one zone, you have one such pointer, so every single free block in that zone is reachable through a one linked list, single linked list. Problem here is there's no way to go back. So there, when you have a heap element, you don't know what zone it came from, what zone it belongs to, and this is a problem especially for performance reasons, because garbage collection on a used heap is very slow that way. Let's come to the allocation. So as I said, when you allocate something, the normal case is you have a free list, and it will just take the first element from the free list, return that, and it's okay. But at some point, your free list will be empty because everything is allocated. So this means the system needs to grow this zone. So a new page is added, and then all the elements in that page are put into the free list. So back then, what would happen is they would put the first element, the second element, third, fourth element into the free list. So that in the end you have a free list that is LIFO. The last freed one, so the last in a page, is returned first. So this means on a normal iOS kernel heap, when you allocate something and there was new memory, it will always be given back to you in a backward fashion. So when you allocate, you get, of course, the element, the pointer is changed, and again, and so on. So basically, you will get the memory backward in a backward fashion, page by page. So now let's go back to dynamic allocations. So we need dynamic allocations, and I already said we use kalloc for that. So the idea is now that kalloc uses a zone allocator internally. So the first thing it needs to do is it registers a lot of zones. You can see them there, like kalloc 16, 32, and so on and so on. And the idea now is that when you allocate, for example, 17 bytes, it will check, oh, what is the size? It's 17. Oh, it does not fit in a 16-byte block, so I have to put it in a 32-byte block. So then kalloc will basically get one element from the kalloc 32 and return that to the user. And this means now that the last 15 bytes in that block are actually unused. They are like padding that is never used. It also means when you later free this, the system must know that you want to free 17 bytes, because otherwise kalloc does not know in what zone it needs to put back this element. And it would be really bad, for example, to put a 17-byte buffer on a 128 bytes free list, because then the next allocation would be a too small buffer, and they would have a buffer overflow. So it's very important to always put it back into the right zone. Okay, so what kind of kalloc zones, what the numbers are, depends on what iOS version you are on, if you're on 32-bit or 64-bit. So during the lifetime of the kernel heap, Apple changed that all the time. In the beginning, there were only powers of 2. Later on, they had some intermediate ones. And this usually has to do with Apple realizing that a certain element is allocated quite often, and it would turn into too much waste on the heap because of all the ends are always unused of the blocks. So they just add a new element and so on. For example, let's assume you had 17 9-bytes allocations. So in the original heap, you would always allocate 128 bytes. And now they have just added the kalloc 80, so you have always only 1 byte waste and not 49. The other way to allocate dynamically is this malloc function, and it basically allows the caller to forget how big a buffer was, because it will just put the size as metadata in front of the data. So when you allocate something, there will always be the size prepended to the data. And again, you see in the end, there's still the same waste because it always needs to fit into a zone. Around this time, this whole allocator was abused in for heap feng shui. Basically, what people did was they were either creating exploit-specific allocation and deallocation primitives. For example, I used opening and closing N-drive sockets. Other people mapped and unmapped file systems. This was the exploit-specific one. Then I presented on using OS unserialized XML, which is a function used by IOKit API functions to take XML and turn it into objects. So you would fill the memory with objects and object pointers, which is really nice for overwriting them, because then you have vtable overrides and you have control over the code. Yeah, so that was the two things that were used at this time. And attackers were normally going after this single linked free list. They were just overwriting the pointer to the next free element. And when you do that, the next allocation will basically make your attacker pointer the head of the free list. And then the next allocation would return an attacker controlled pointer as the memory block. And then the kernel would write something into it. So you had an arbitrary write anywhere. The other thing people attacked were the size fields of something like malloc, because then you can confuse the k-free to put the block back into the wrong zone. Keep in mind, when you put a 17-byte block into a 128-byte zone, then the next allocation in 128 will actually just return a 17-byte block, and then it will overflow. The other thing was, especially after OS unserialized XML, you could just overwrite vtable pointers and then get code execution that way. Okay, so that was a time when iOS had, the kernel had no mitigation whatsoever. Then Apple started adding mitigations. So when iOS 6 was released, they made some changes to OS unserialized XML that actually had very little impact on being useful for exploitation, but it fooled some people to believe it fixed the problem. But actually, you can still use the function today. The next thing they did was they randomized the initial allocations so that now the whole zone memory is randomized, because it's like something of random bytes is allocated before that, so the position of the zone map is no longer the same after every boot. The next thing is they protected the single free list against overrides, and small memory blocks get poisoned. That means they get overwritten, so you cannot rely on their content after you free them. But we get into this in detail. So this override protection of the free list was implemented by creating two random cookies in the kernel. They are called no poison cookie and poisoned cookie. And the lowest bit basically distinguishes which of the cookies it is. And the idea now is that when a block is freed, the first for a few bytes are still the pointer to the next free block. But the last few bytes are used as a cookie that basically encodes the same pointer XORed with one of the two cookies. And during usage of that free memory later on, the kernel can distinguish if it's the right cookie not if it's the right cookie, if it's one of the cookies, or if it's a wrong cookie value at this point, and then you can panic and say, oh, this was modified heap, there's an overflow, game over. So basically this was a protection against a simple override of the pointer, because you can only override the pointer if you can make it a real cookie at the end, and you can normally not do that because it's a random value unless you leak it. So if you leak the pointer, you could still, if you leak the whole block, you could still calculate the cookie by taking the plaintext pointer, taking the cookie with the pointer, XORing them, and then you have the cookie, and then you can prepare whatever you want later on. So the next thing Apple did was, because they have now these cookie and pointers and so on, they obviously wanted this to be protected against info leaks. So now when you allocate a block on the memory, the first bytes and the last bytes will be overwritten by deadbeef, so that you, if the code that is calling this accidentally leaks this data directly to user land, it will have no impact on the protection of the cookies because they are now overwritten. The next thing is they created this poisoning. This was actually a feature you could always activate in a debug kernel, so you could always say that, tell the system, oh, please poison all memory that is freed. But at this point, they actually decided, okay, let's activate this by default on release kernels as long the block is small. So normally it's a cache size of it's normally 64 bytes for the processors. So every block smaller equals 64 bytes is poisoned when you free it. That means it uses the same kind of pointer cookie, but it uses the poison cookie for that, and everything in between is overwritten with deadbeef. And when you later allocate this block again, it will see, oh, this is the poison cookie, so everything in between must be deadbeef, and it actually checks that everything is deadbeef, otherwise it panics. So this means around the time of iOS 6, people were now using different ways to attack this. So around this time, Mark Dowd did his talk with Taji Mand on iOS 6, and they introduced a new heap feng shui method that is called VMAP copy-t. Basically, the idea is that you're sending most of the time Mach messages with out-of-line data. They would then create this structures in kernel memory, and because you control how much bytes are sent, you basically control the size of these allocations, and you control most of the data except for the small header. And you can also free these, so you have very good control over the heap. And basically between iOS 6 and maybe 9, every single jailbreak was using this. And even in 10, you can still kind of use it, but not in the same way. And the other thing is, which Tajay and Mark Dowd basically explained, is the header of these structures has a few interesting fields like pointers and sizes. And if you would now target them with an override, you could turn a small overflow into a large overflow, or you could just create arbitrary info leaks. At the same time, people would also still go after other things like override the size field of malloc, so get freeze into the wrong zone, or they would still go directly after the vtables of objects in kernel memory. So then Apple released iOS 7, and there were basically two changes to the heap, one small, one big one. First of all, they now start to poison even larger blocks. And they introduced this new heap pagelets feature that is most likely not caused by security, just by performance reasons. So first, the large block poisoning. There is a debugging functionality in the iOS kernel that's called setPfactor. You could always activate that if you could set boot arguments, but with iOS 7, Apple actually activates it by default and initializes it to a random value. So this random value is either 15, 16, or 17, and in 25% of the cases it's 15, in 50% of the cases 16, and in 25 cases it's 17. So what does it do? So basically every zone has a counter that is called its ZP count. And every time you free an element in a zone, it will increase this counter. And every time this counter reaches the ZP factor value, it will poison this block no matter if it's small or big. That means, let's say in 50% of the cases, every 16th free in any zone will result in a poison block, no matter how big the block is. It's small or big. Yeah, but for every zone this is separately, and there's only one randomness per boot, so this does not change over time. It's always the same value, 15, 16, or 17. The other change was way bigger. So Apple realized that this whole garbage collection thing is really hard when you have no way from an element back to the zone. So they started to create page metadata, and they called this feature the page list feature. What they did is they added new lists or queues of pages to the zone structure. And now the zone always keeps lists of pages that belong to that specific zone. And as you can see here, it's a double linked list. So you can go in both directions through all the pages that belong to each zone. Furthermore, what they did is they added page metadata to the end of every page. The problem with this is they decided to not use that for everything. They only use it for a small subset of zones. So a lot of interesting zones for attackers don't use this new feature. And in some cases, the attacker can actually choose if he wants to go after a new feature or old feature. So what does this metadata do? So basically the idea is that the metadata now contains a back pointer to the zone. So now when you have an element, you go to the page metadata, so you then know what zone this element belongs to. The next thing is, because now everything is page related, there's no global free list for a zone anymore. Now there's a free list for every single page. So you see the blue one is now the free list of that specific page. Of course, all the pages need to be linked to each other, so there's a double linked list between all those pages. And every page contains a counter how many free elements are currently in the free list. And it has a counter how many elements fit into one page. So allo count might be misleading. It does not mean how many are allocated. It means how many elements fit into that one page. So now all the memory is basically put in page lists, but it's not one page list. Apple has 4 page lists for every zone. And the idea is they have a list where all the pages are in that are completely full at the moment because they're fully allocated. They have one that is all free, so every single element in that page is free. They have one where there's partially free and partially used. That's called intermediate. And for some very few special zones, they have this any free foreign list, because a very few special zones allow you to free memory into the zone that is actually not from the zone map. So that is memory somewhere on the heap. So there's only very few zones that allow this. And for that, they have this forced list. Now it's up to iOS and the allocator to always ensure that a page moves around to be always in the right of these queues. So when a page gets completely full, it needs to be removed from whatever page it was on at the moment, from other list it was on, and it needs to be put into all used queue, and so on and so on. This means now when you allocate an element, what happens is the allocator goes through the any free foreign, the intermediate one, and the all free list, and tries to get the first available page in that area. So normally it would get the first intermediate page, so that is partially full and partially empty. It will take the first page, select it, and then go to the free list and return the first element from that. If no such intermediate page exists, it will search a page that is all free. It will get to the all free first page, will take it, will get the first element, and go on. Sometimes your heap is completely full, then that means all these lists basically are empty. Everything is in the all used one. So in this case, it will add a new page to the system and then put all of this into the all free page queue and then restart this algorithm. Free, on the other hand, will just go to the element, see what page it belongs to, put it on the free list, and then just ensure that the page stays on the right queue. So for example, it could go from the intermediate to the all free because suddenly all the elements are freed on a page, or previously the whole page was full, now one element is freed, so it needs to be put from all used to intermediate. But this happens automatically in the background. So what is the impact on exploitation in iOS 7? Well, the general impact is, first of all, garbage collection in these kind of zones got really easy because the system keeps a list of pages that are completely empty. So the garbage collector can directly take these pages and return them to the system. It's a lot faster than just trying to find out which pages are full and which are empty. It also means that free operations are now always local to each page they're on. That means in the global context of heap feng shui, frees by other threads don't interrupt you as much as before. Allocs, on the other hand, interrupt you no matter where they are, because they always deal with the first page that is currently in a specific queue. So they will always allocate in the same page you are currently in. But this is not much different from before, because before you always needed to stay in the same page anyway. So other threads were allocating at the same time. So they would interrupt you in the same way they do right now. The others, just the freeze of other threads are now interrupting you not so much anymore. However, Apple did a very, very big mistake because this metadata they created and the queues were double linked lists that had absolutely no exploit protection. Keep in mind, this is 3 years ago. So 3 years ago, Apple filled the whole kernel heap with double linked lists that had no protection against safe unlinks. Well, they had no safe unlinks. So with iOS 7, kernel heap exploits in iOS got really easy to exploit, really easy. Also, because of the new page list feature, there's now a new attack that is going on. It's now the idea to confuse the allocator to free elements from pages, from zones that use the new feature into zones that use the old feature and vice versa. So there's now the possibility to get more confusion. Of course, Apple was aware of this possibility that you free something into the wrong zone. So they added this code to the system. What they basically do here is, and this is the only slide with a lot of code, what they do is they detect when you try to free an element into the wrong zone. How can they do that? Because they can just go to the element, go to the page metadata, take the zone pointer, compare it to the one that you try to free it to, and when this does not match, then it's obviously a problem. It's a heap corruption. So Apple detects the heap corruption at this point, and the same thing would be to just panic. But Apple does differently. They first try to repair this corruption by determining if this zone pointer that they found with the element is actually a legal one. And when they find it in the list of zones, they will just now change the allocator to free that into the right zone, according to the metadata. But if they cannot repair it, so imagine they have detected a kernel memory corruption, and they say, okay, we cannot repair it, so let the code just run. So they detect that there's a memory corruption and just let it run. Both things are stupid. The letting it run, of course, is stupid, but the other thing, the repair, is also stupid because when you try to free a page list element into a free list element, a page list zone element into a free list zone element, then this metadata, this thing here tries to parse, is actually attacker control stuff. So the attacker can put whatever zone pointer it wants in there, and then this repair algorithm will actually help the attacker and put this element into the wrong zone, and this is really bad. Yeah, so people use that. Heap feng shui, they basically used in iOS 7 the same as before. And for corruption targets, everything worked the same in iOS 7 as before. But the new target were these double linked lists because they gave you arbitrary bytes anywhere for very little work. Really, it got really easy to write exploits that way. Okay, let's go to iOS 8. In iOS 8, Apple, maybe because of Tarjay von Azimuth, because he was talking about this, they started hardening these queues, as we will see later. And they maybe also realized that poisoning every 16th block is a little bit much and makes the system slow. So they deal with that. So the first thing is they made this queue hardening. So they basically sneaked into the very, very, very last beta of iOS 8, sneaked this new protection that every single queue macro had now a safe unlink protection in, and they were using these macros in many places, not only in the heap. So suddenly, in the very last beta, you had a lot of safe unlinks in the system that were not there before. So this means you can no longer overflow this because the safe unlink will detect the overflow. The next thing they introduced is this ZP scale feature. The idea here is that poisoning every 16th allocation, maybe in a, like, let's say 2048 byte block, is a lot of memory that gets overwritten with dead beef, and it maybe takes a lot of time. So the most likely reason why Apple did this is to make the system faster again. So what they did is they change how often they poison the block, and they do this by introducing ZP scale, which is by default 4. So what they do is they take the size, let's say 1024, and then they divide it by 16, which is 128, no, 64. So it should be 64, if I'm not completely wrong at the moment. Well, let's use the number on the slides. It's easier. So it takes 256, divides it by 16, so we have 16. So what it does now is it adds this number to the ZP factor. So this means now 256 byte blocks are only poisoned every 31, 32, or 33 frees. And the bigger the block gets, the less often the poisoning happens. This means for people who do use after free exploits and rely on the content being intact after the free, it got suddenly easier again because the poisoning gets less often the larger your block is. So how do people attack this? Again, for heap feng shui, actually nothing changed. You can no longer go after the double linked list in iOS 8 because of the safe unlinked, but everything else worked as before. Let's switch to iOS 9. Apple started hardening this VMAP copy T structure that was used by all the jailbreaks. They started changing the position of the metadata, and they now started with one of the latest iOS 9 versions to randomize something in the heap. We will see. So the hardening they did was they took this VMAP copy T structure that was used for the kernel buffers, and inside the structures were a data pointer that was completely useless because normally it should always point directly after the header. So it was basically easily calculated, this pointer, and it was really bad to have it in there because people could corrupt it and use it for info leaks. The next thing is they had not one, they had two size fields in the structure, and this attacking these two size fields allowed to either have a very nice info leak or to confuse the heap allocator when it put on the zone later on. So Apple removed also that size field. Also, they removed a bunch of unused stuff for kernel buffers. So they made this VMware copy T structure very small. This is actually nice for an attacker because the smaller the structure is, then you can suddenly start to use it for heap feng shui in the small zones. Previously, it was quite a large header, so you had like at least 88 bytes on 64-bit system. You couldn't control any zone smaller. Now it's 24 bytes, so you can use it for smaller heap feng shui. The next thing is, because so many people were using it for arbitrary info leaks, Apple now checks a hard-coded 4 kilobyte limit. So if you try to have a VMAP copy T structure that has a size field larger than 4 kilobyte, this is resulting in a kernel panic. Also, they have now in several places where they make use of this kind of structure, they have a size field in an additional position, and then they compare the size field of, for example, a Mach message with the size field in that VMAP copy T, and if they don't match, it's obviously manipulated, and then it's also panicking out. So they made it less usable, but they only made it less usable for info leaks and for buffer overflows. For heap feng shui, it's the same usable. So you can still control the heap with that. The next thing that I didn't actually realize for a very, very long time, because I was never dealing around with it, between iOS 8 and iOS 9, they suddenly moved this metadata that was previously at the end of the page. It suddenly moved to the beginning of the page. So most probably the reason for that is to protect it against buffer overflows, because if it's before you, you cannot overflow into it, you can maybe only underflow into it. The most strange change they did in iOS 9.2, because they started to modify the free list generation. So remember, when you had a new, when the zone grew and you had a new element, you had a new zone page, the first thing it needs to do, it needs to create a free list for that specific page. So what it normally would do, it would take the first element, the second element, and so on, put them in the free list, and then because of LIFO, the first element would be returned last, and so on, and the last element would be returned first. So this gave the heap a very predictable order. With iOS 9.2, they changed that. Actually, I hope it's 9.2, not 9.2.1. I think it's 9.2. So they changed that. What they do now is, whenever they do this after another, so what they do now is, they create this free list, and every time they need a new element in the free list, they throw a coin, and the random decision is made, should the first element in the page or the last one be added to the free list. So let's say we add the last point to the free list, so now the head of the free list points to that one. Now it throws the coin again, but this time it says take the first one. So it will look like this, and this continues, like always a random decision if it takes the first one or the last one. And so in the end, what you end up with is, whenever a new page is added to the heap, the initial free list is random. So you can no longer predict where it actually ends up. There are some probabilities, like if you allocate quite late, you will never end up most probably in the end of the zone page, but there's all probabilities. There's no insurance anymore. So how did people abuse that? For heap feng shui, they basically used most of the same routines. As I said, VMAP copy T, also it was hardened. It still works as before in the regards of heap feng shui. Just for the corruptions, they could now only use smaller leaks, and they had to use different functions to not run into size limits. Size comparisons. But mostly it was the same. And if you go after metadata or application data, nothing changed in iOS 9. Let's go to iOS 10, and I'm actually running out of time, but it should fit. So Apple started hardening VMAP copy T more, but again, what they mostly did is they enforce more checks to validate that you're not overwriting the size and so on. They do this in more places. For heap feng shui, they still will not do anything just for overwriting. They now use the fixed zone structure array. They completely revamped the page metadata. They now changed the free list against overwrites and leaks. They don't use inbound metadata anymore anywhere in the wrappers. They now have external metadata. And they changed the zone allocator debugging features. So the first thing they did is they moved all the zone structures that were previously on the heap. They now moved them into a fixed size zone array that is in the data BSS segment for iOS kernels. And this means all zones are now at a fixed address in the kernel relative to the kernel base, which is maybe not a really good idea, but they did it anyway. So previously you wouldn't know where a specific zone is, now you know where it is in memory. I mean the zone structure. The next thing is, when they allocate this zone map, they now additionally reserve memory in that zone map that is called the zone metadata region. And because it's the first allocation, it should be in the beginning. And what this contains is basically metadata for every single page in the zone map. So now for every single page there is external metadata. This now means every zone can make use of metadata. This metadata looks like this. It's 24 bytes on a 64-bit system, and they distinguish between what they call real metadata and apparently not real metadata. And the idea here is that because of the allocation size, so that was the thing that how much does a zone grow whenever it runs out of space, it might grow by more than one page. So the idea is the very first page is real metadata, and every other page is additional metadata. So it does not get the full metadata, it only gets back pointers to the real one. So the idea is, when you are on the second, third, or fourth page of an allocation size, the only fields that are filled out is the set index, which says 256 means, oh, this is like a secondary page. And then the offset is, how many bytes do you need to go backward from the beginning of this metadata to get to our page 0. And then page 0 contains forward backward pointers inside the page list. It contains a free count as before. It does not have a zone pointer anymore because now the zones are in the static array. So it just has a 1 byte index into that static array, so you know what zone this page belongs to. And page count is how many pages fit into one allocation size. So whenever the zone grows, how many pages are there. The free list offset is also new. Instead of having a pointer to the very first free element of that specific page, they now have a 32-bit offset that just says how many bytes from the beginning of that page is the first free element in this page. So they basically removed all the pointers from there, except for the page list pointers that are protected by Save Unlink Anywhere. So when you leak this information here now, you actually have no idea about the pointers. Might be one of the reasons for the design. I think it's mostly like to make the whole thing smaller because you have so much metadata now, so you want to have a smaller amount of this data. So inside a page, they also changed stuff because now, as I said, they now have this free list offset instead of the pointer. So it will tell you how many bytes from the beginning of the page is the head of the free list. That's the first change they did. But they did another change. Previously, the beginning of the page would be a pointer to the next block, and the next block, and the next block, and then in the end null. So they changed that now so that at the beginning of these free elements, there's never a plain text pointer. Instead, it's always the pointer XORed with a no poison cookie. And then in the end, the backup pointer is still the pointer XORed the cookie, and there they use still the no poison or poison cookie to determine if it's a poison block or not. But the first pointer is always obfuscated now. So why did they do that? There might be many reasons. One reason is you don't leak the cookie anymore when you leak the full content of the block anymore, because both are either the same value or XORed with two random values, so you cannot get to the cookie value that way. But the more important thing here is maybe caused by Google, because Ian Beer from Google basically told Apple or told the public that having the pointer in the beginning is really, really, really bad, because when you type confuse an empty block for an IOKit object, the first pointer is used as a pointer to the V table. So if your free block is actually confused as an IOKit object, it will point to a next free block. And if you have a V table in that free block, then you could easily type confuse an empty block for an actually valid object, and then you had code execution, which made race conditioning use after free in the iOS kernel quite easy to exploit in some cases. So this is not possible anymore. There's no real pointer in the beginning anymore. The next thing, and this is most probably the worst part of it all, is now when you have an element, you can always get to the metadata for this element. So you always know for every buffer what zone it belongs to. That means the allocator can always check that you try to free it into the right zone. If you don't try to free it in the right zone, then it's easily detectable by comparing the zone index to the actual one that you wanted to free it to. And this means the whole attack class of freeing something into the wrong zone is no longer possible. So a lot of attacks that are used in the wild don't work anymore. It doesn't mean it's not exploitable, because you can still go after other things like application data, but the most used attack is not possible anymore. Also, because now all the elements basically have a zone assigned, the size is always known because you know how big the elements of a specific zone are. So all these wrappers don't need to really keep track of the size anymore. For Kerlak, it's kind of doesn't matter, but for malloc, it means this size field in the beginning is completely superfluous. It doesn't need it anymore, and that means malloc was basically changed by Apple to be just an even simpler wrapper around kalloc, and so this metadata, the size field, is gone. It's not there anymore. They also did the same change to KernOS malloc, which is basically copy and paste of malloc. And the funny thing here was when I did my talks for iOS 5, I basically said on stage with Apple people in front that KernOS malloc, because it was copy and paste, had a possible integer overflow in it. And 5 years later, that's now fixed. So the thing is, there's no size field now anymore. And this is actually good and bad for an attacker. It's bad because you cannot override it anymore, but it doesn't matter because these free into the wrong zone doesn't work anymore anyway. But now the good thing is, because there's no size field anymore, the whole thing is just data used by whatever the kernel puts into the allocated data. This means you now have way, way more code paths in the kernel that will take attacker data and put it into the heap. Previously, you always had this annoying size field in front of it, so you could not create arbitrary structures, especially objects in the kernel, because the first size field would always be taken as a pointer. So now, with this metadata gone, you have way more code paths that allow you to put arbitrary data into the heap so that you can then use for type confusion and everything else. So the last thing, Apple also revamped the debugging functionality. Remember, you had this boot arguments to allocate to lock the heap allocations and deallocations, but it was limited to one single zone, and Apple changed that to now you are now allowed to lock up to 5 zones, but this is again just the limit in the kernel. Theoretically, the code is now able to lock all zones at the same time. The boot arguments that you use for that is setlock 1, 2, 3, 4, and 5, and you can just give it different zones and they will be locked at the same time. If a zone is locked to or not is defined in the zone structure. So there's a bit now that explains if it's locked or not. And what they also introduced is this setlock btlog pointer in the end. So now every zone structure can point to its own btlog. That's why the code is actually able to lock all zones at the same time. But for speed reasons, it's just limited to 5. The other thing is, and I haven't researched that too much, is the structure of the btlog is now completely different. They changed the simple ring buffer into something that uses hash tables with MD5 as a hash function and all this kind of thing. It's most probably also used for speed and so on. But this is a more complicated thing that haven't fully documented yet. So my prediction is that for simple Feng Shui, all the previous methods will work. You will have new methods because now you can also use everything that uses malloc. And there's, for example, a possibility with POSIX spawn to actually malloc whatever you want into the kernel, so you can fill the kernel with whatever data you want just by using POSIX spawn and some specific flags. The corruption targets, every size field is now becoming uninteresting because you cannot free into the wrong zone. It might be still interesting for like info leaking, but not for the free into wrong zone one. But everybody who was already attacking application data like pointers to objects, for them, nothing changed. Maybe one thing we will see in future is that people not attack the pointers to objects, but the pointers to Mach ports, because then they can create themselves really funny internal things that the system loves. And then you can create pointers to things that are usable by the system directly. Yeah, just to explain, for example, when you have a task like the kernel task and you create yourself a Mach port for that, then you can read and write in it and so on. These are things you can still go after, and Apple hasn't done anything to that at the moment, unless I didn't see it in the iOS 10 kernel. Yeah, so we ran actually out of time. We overran a little bit. So any questions before you go into the break?
Regarding the large block poisoning,
yes,
which is happens sometimes.
Yes.
What's the point of poisoning sometimes versus a jailbreak, which can be tried many times?
Well, the thing is, usually what you do is, when you have a use after free, your exploit might rely on the fact that the content of a freed block is still the same that it was before. And when you have a random poisoning, then the content might actually be just that beef. And when you now access it, it will access maybe pointers that are now dead beef, and it will crash the system. That's the problem. If you have like a random poisoning and your exploit relied on heap stuff being intact after free, then...
I understand. What I'm asking is, if you're talking about a statistical poisoning or random poisoning,
yeah,
it almost seems like this seems to mitigate attacks in the wild, but not jailbreaks, which you can try again and again.
Oh, yeah. Well, the thing is, yeah, nowadays the jailbreaks actually have things like boot loops or so they just do the same exploit over and over again. But if you want to have a clean exploit, this will be a problem. So as long as you have something that you just loop and loop and loop, it's fine. You can still do it. Like there's this joke that I did on Twitter where there was this one movie file. When you open it on your iPhone, the kernel would crash. And people were like saying, I was telling, oh, this is a new jailbreak, and you just click it. And people were clicking it, and then after they say, oh, it's just crashing, I told them, yeah, you just need to try it over and over again. And people were telling me then, I tried it like 20 times and it still does not work. Yeah, but it's true, it's just like a statistically probability. And there's always this quote from Dave Vitale that he made like many years ago. If you just have a 1 in 256 chance, just send the exploit to 1 million hosts, and there's still a lot of systems, yeah.
Any other questions? Maybe others will be off stage. Thank you very much, Stefan.